Let's continue with some sample problems concerning the unit circle. Our first slide, evaluating a circular function. Circular function values of real numbers are obtained in the same manner as trig function values of angle measured in radians. So what we've done before with finding coterminal angles and reference angles is going to be the same procedure as followed in this section. This applies to both methods of finding exact values such as reference angles analysis and calculator approximations. But when we use calculator approximations, they must be in radian mode when finding these circular function values. Our first example asks us to find exact circular function values. If we're given the exact values of sine of 7 pi over 4, cosine of 7 pi over 4, and tangent of 7 pi over 4. Here, the first thing that I want to do is to convert my radian measure into a degree. To do that, we're going to take 7 pi over 4 and multiply by 180 over pi. And when I simplify this problem out, I'm going to get 315 degrees. Now what I'm going to do is the same thing I've done in the past sections, is I'm going to kind of draw this up on a coordinate plane. And I'm going to identify an initial angle on my x-axis, and then I'm going to draw in my 315 degree angle. That will give us an angle in the fourth quadrant. Then I'll create a reference angle to my x-axis. That will give me a 45 degree angle. That will generate a special right triangle, which is my 45, 45, 90 right triangle. Let's keep in mind that this is going to be drawn inside of a unit circle. Therefore, my radius in a unit circle is always going to be equal to 1. From this, I can determine the leg measures by taking my hypotenuse and dividing by the square root of 2. So 1 divided by the square root of 2. And when I rationalize, that will give me the square root of 2 over 2. But remember that I am in fourth quadrant, and the y value is going to be negative. Also recall that since this is a 45, 45, 90 triangle, that the legs are congruent. Therefore, my x value is the square root of 2 over 2. And my x is going to be positive, even though this is in fourth quadrant. Now, all I have to do is to complete the problem by solving for my trig ratios, or in here, my trig functions. So the sine of 7 pi over 4 is going to equal my y value in the fourth quadrant. In this circumstance, it will be a negative square root of 2 over 2. Cosine of 7 pi over 4 is my x value, which is the square root of 2 over 2. And the tangent of 7 pi over 4, which is going to be y over x, which is going to be the square root of 2 over 2 divided by the square root of 2 over 2, which if I simplify this will be 1. But remember, my y value is negative, therefore my answer for tangent of 7 pi over 4 is equal to a negative 1. If I refer back to my unit circle, I can see if I have an initial side of an angle, and then I draw in my 315 degree terminating side of the angle, I end up at 7 pi over 4, which gives me an x value of square root of 2 over 2, a y value which is a negative square root of 2 over 2. Then I can use my definitions of circular functions to find sine, cosine, tangent, or their reciprocal functions. Our next example wants us to find a calculator approximation to 4 decimal places for each circular function. Make sure when you do this that the calculator is in radian mode. Notice that our examples show us cosine of 2.01, cosine of 0.6207, and cotangent of 1.2071. These are written in radian measure, not with the symbol pi, but just radians alone. What we need to do is take a look at a unit circle and see exactly how the radians are created without pi. Here we have a unit circle that has all radian measures, not degrees. But these radian measures are written in terms of the symbol pi. But what we want to do is find out exactly what 1 radian, 2 radian, or even 6.28 radians would look like. Well, let's start out with the initial angle, and this would be at 0 degrees or 0 radians. As we continue through the circle, all I need to do is actually take pi and divide by 6, and that will give us a value of a radian. So in my calculator, all I would have to do is hit pi and divide by 6. So pi over 6 is approximately 0.52 radians. In this position, this could be called pi over 6 radians or 0.52 radians. With that idea, let's just substitute our values in for our quadrant angles, and therefore we will know where our radians lie within a specific quadrant. So at 90 degrees or pi over 2, I'm just going to take pi and divide by 2. This will give us 1.57 radians, or pi over 2 radians. I know that pi itself is 3.14, so at 180 degrees, this is 3.14 radians. And I can find my radian at 270 degrees, which will be 4.71 radians. And I know that this is 2 pi, or 2 times 3.14 is 6.28 radians for a complete revolution. Now, for radians that fall between 0 and 1.57, I know that I am going to be in quadrant 1. For radians that fall between 1.57 and 3.14, I'll be in quadrant 2. Between 3.14 and 4.71, I'll be in quadrant 3, and 4.71 and 6.28, I'll be in quadrant 4. Therefore, I'll be able to determine my values of positive and negative for my x, y, depending on which quadrant I lie in. So our first example is cosine of 2.01 radians. If we go back to our unit circle, I know that 2.01 is going to fall between 1.57 and 3.14. Therefore, my angle of 2.01 radians is in quadrant 2. Now, all I need to do is to substitute this in the calculator, remembering I must put my calculator in radian mode. To do that, I'm just going to hit mode, and then I'll scroll down until radian is highlighted. I'll hit enter. Now my radian is highlighted and blinking. Hit clear, and then I can solve my problem. Then all I need to do is enter cosine 0.201, and I can then get my value to be a negative 0.4252. Since this is in quadrant 2 and cosine is a value of x, I know that my term is going to be negative. Example B, cosine of 0.6207. I know that that is going to be between 0 and 1.57, and therefore this is going to be in quadrant 1, and I know that this is going to be a positive value because my x value is positive. All we need to do is substitute into a calculator. And when I do that, my approximation for cosine 0.6207 radians is going to be 0.8135. Example C has me finding cotangent of 1.2071 radians. 1.2071 is going to fall between 0 and 1.57. Therefore, this is going to be in quadrant 1. Cotangent is going to be x over y, and that would be positive over positive, so my solution should be positive. And when I enter this into the calculator, I should get an approximation to be 0.3806. Our next example, without using a calculator, decide whether each function value is positive or negative. Consider the radian measure of the quadrant angles. Our first example, cosine of a negative 2 radians. From our previous example, we have our radians not written in terms of pi. Therefore, we can associate negative 2 radians to our given unit circle. This is written counterclockwise measurement, but we can go backwards, understanding that a negative 2 radians would have me fall into quadrant 3. Very similar if I went clockwise, 2 radians would fall between 1.57 and 3.14. If I go counterclockwise, that would put me in quadrant 3. So my example asked me to find the cosine of a -2. This will be in quadrant 3. I'm looking for an x value being cosine, therefore my solution will be negative. The tangent of 2.5, if I go back to my unit circle, 2.5 radian angle would fall between 1.57 and 3.14, which would be in quadrant 2. Therefore, this would be y divided by x, which would be positive divided by a negative, and again, my solution would be a negative value. Secant is cosine reciprocal. Therefore, this is going to be 1 over x, and 4 radians is going to fall between 3.14 radians and 4.71. Therefore, this will be in quadrant 3. So my value for secant 4 radians is going to be in quadrant 3. My x value is negative, so this is also a negative solution. Our next example shows a figure that has an angle theta in standard position with its terminal side intersecting the unit circle. Therefore, I know that my r is going to have a measure of 1. We want to evaluate the 6 circular functions of theta. From previous slides, we know the definition of circular functions. So here, we know that the sine of theta is going to equal y. Our point on the terminating side for y is a -1/2. Cosine theta in a circular function has a value of x. And therefore, my x value on the point of the terminating side of my angle is a -1/2. Tangent theta is going to equal y over x, which is a -1/2 divided by a -1/2. And we know that anything divided by itself is 1, and a negative divided by a negative is a positive. Remember that we are allowed to do this in circular functions because our values of r in each one of my 2 functions of sine and cosine has a measure of 1 because we're inside the unit circle. So, for cosecant theta, the reciprocal will be a -2. For secant theta, the reciprocal again will be a -2. And for cotangent theta, a 1. My last example wants us to find the value of s in the given interval that has the given circular function value. Do not use a calculator. Here our interval is going to be between 0 and 90 degrees. And they want me to find a value of s, or a degree for s, that matches a circular function of square root of 3 over 2. I've created 3 coordinate planes that have a central angle of my special triangles that I've been using in this section. 30, 60, 90 with a 30-degree central angle, 45, 45, 90 with a 45-degree central angle, and a 60-degree central angle, which still corresponds to a 30, 60, 90 triangle. Knowing that I'm in a unit circle, I'm going to know that my r value on each one of these coordinate planes is 1. Let's solve for the short leg on my first triangle. When I do that, I take the r, divide by 2. My y value is a 1/2. The sine of y needs to be the square root of 2 over 2 here. Therefore, this does not correspond. The second coordinate plane has a central angle of 45. A 45, 45, 90 triangle, I can find the measure of the y value of this leg by dividing the r value by the square root of 2. Therefore, 1 divided by the square root of 2, and when I rationalize, I get the square root of 2 over 2. That does not correspond to a circular function value of the square root of 3 over 2. In my last coordinate plane, I have a central angle of 60 degrees. I need to find my short leg, which is opposite my 30-degree angle. I'm going to take my r value and divide by 2. That gives me a 1/2. But to determine my y value for sine, I need to take my short leg times the square root of 3. That gives me square root of 3 over 2 for the value of y. Sine s is the value of y. These 2 values correspond. Therefore, the s value I need is going to be 60 degrees.